Hey guys, welcome to your first of two Chapter 15 videos. In this video we're going to look at the following. We're going to come up with a generalized rule for addition when we're talking about probability. In Chapter 14 we had an addition rule, but there were restrictions on it. You had to have disjoint events for it to work. We're going to fix that today. We're going to look at conditional probability just a little bit. We're going to introduce it. It'll be important throughout the discussion today, but we're going to continue that discussion in the Chapter 15 Part 2 video when we work with the Bayes theorem some. We're going to look at a fixed rule for multiplication, just as with the rule we had for addition for probabilistic events in Chapter 14. We did have a rule in 14 for multiplication, but it depended upon independence. We're going to fix that. And we're going to define independence in the last part of the video. Okay, so let's start with example 1 here. We've got the following. They say, let A be the event that we've selected a brown M&M, and let B be the event that we've not selected a blue M&M. Okay, so if the probability that selecting a brown M&M is 15%, the probability of not selecting a blue M&M is 80%, what's the probability of A union B? Now, some of you guys change the color scheme. Well, keep the current color scheme, don't show the message. Okay, some of you guys will realize instantaneously why doing what I'm about to do is a mistake. This is the method we would have used last chapter. We would say, oh, okay, well, let's just kind of wave our hands a little bit. Let's assume that they're disjoint events when they're not. So the probability of A plus the probability of B would take me to my answer. That would give us 0.15 plus 0.80, which is 0.95. Okay, well, why doesn't that work? Well, this is bad for the following reason. Let's change to a different color to represent the fact that we're going to solve this correctly now. Let's represent all the M&M colors that we can choose from a bag with the following sample space box. Okay, so I'll represent with a large circle. That in that circle are all the ways we could not select a blue M&M. So this is for event B, and we know that the probability of event B occurring is 80%. Okay, well, selecting a brown M&M is well, let's back up. Anytime we don't select a blue M&M, there's a chance that we're selecting a brown M&M. Therefore, within this box representing the colors that we choose from the M&M bag, within the large circle is a separate circle, wholly contained within that larger circle, for event A, that we select a brown M&M, and we said that that probability was 15%. Okay, so the problem with what we did in red is that you're effectively adding that small circle probability together 2 times, because that 15% is included within the 80% already. Okay, so we can fix the general addition rule by doing the following. We can say the probability that we want of A union B is still the probability of A plus the probability of B minus the probability of their intersection. That is to say, we can take the probability of a brown M&M, add that to the probability of not blue, and then subtract off all the cases in which you have both occurring. Well, you only have both occurring anytime you have a brown M&M. So our general addition rule, which this is in blue that you're looking at right now, says that to answer this problem we have the following. We have a 15% chance of brown plus an 80% chance of not blue. Subtract off when they both happen, which is the 15%, which takes you to a final answer of 80%. Okay? And there you go. And that should conform to our expectations. We know, well, everything not within these circles would be when you have a blue M&M. And if not selecting a blue M&M occurs 80% of the time, 20% of the time you've got blue M&Ms. So the probability of A or B occurs 80%. Separate from that, the complement of that 80% is the 20%. So our sample space adds up to 1. Our math is correct. Okay, so there is your general addition rule, which I'll put in the box. That's a key idea for chapter 15. Okay, moving on. Let's now go to, let's see. Oh, we're going to do basically the same idea, just with the second example. Let's say that event A is selecting a blue or green M&M. Event B is selecting a red or green M&M. If the probability of A is blah, the probability of B is blah, and A intersect B is 20%, what's the probability that A or B occurs? Well, once again, let's draw a Venn diagram to represent the sample space of colors that we can choose from the M&M bag. Here we have A, which is blue or green. We know the probability of A is 55%, okay? Separate from that, well, kind of separate, is red or green. Well, they both have green within those circles, okay? So here's event B, which occurs 45% of the time. So, to answer this question of the probability of A or B, probability of A union B, again, we can say, well, the general addition rule says just add the two separate probabilities of A plus the probability of B, and then subtract off any time they're both occurring, which I'm highlighting with sort of this green oval here, okay? We're going to subtract that off because the probability of A includes that green oval, the probability of B includes that green oval. So if all I did was add these two together, again, I would be adding that green oval twice, that green probability twice. We don't want that, so we're going to subtract it off. The probability of A intersect B. So we have as follows. We've got 55% plus 45% minus 20%. That is 100% minus 20% is 80%. Oh, okay. So in this, apparently, in this collection of M&Ms, we have 20% chance of getting not blue, green, or red. Okay, so there's a second example of the general addition rule at work. All right, let's go on to the next slide. We've got 5 slides here in all. In the next slide, we're going to start to talk about conditional probability, and we're going to do that in the M&M context. I think that the M&M context, I can continue to get some life out of it for probably the rest of chapter 15. I think it helps to talk about the same type of example over and over again so that we're focusing just on the probability rules, not losing ourselves in the description of the problem. All right, so in example 3, suppose you take red, green, and blue M&Ms from both a peanut M&M and a regular chocolate M&M bag and dump them into a cup for anyone to nibble on. Out of curiosity, you take each individual M&M from the cup and find the results below in the contingency table, or as you may remember it being called, a two-way table. We've got two variables that are being recorded for all 390 of these M&Ms, and those two variables are either the color of the M&M or that is the chocolate versus peanut, the type of M&M, okay? All right, so from this contingency table, let's answer some questions. If A is the event that we have a red M&M and B is the event that we have a chocolate M&M, so that's two different outcomes, or not outcomes, two different characteristics for each of those two different variables. What's the probability of A intersect B? That is to say that we've chosen a red chocolate M&M. All right, well, you can answer that by doing the following. You can just say, well, A intersect B. There are a total of 48 red chocolate M&Ms, and there are, we know, 390 total M&Ms in the cup, so there must therefore be 12.31% of the M&Ms satisfying both conditions, okay? That's going to be useful when we get to part 3 here in a bit. All right, let's talk about the probability of A alone, that we've chosen a red M&M. Well, the probability that we've chosen a red M&M, look at your marginal distribution here. On the bottom row, separate from the total, separate from the 390, you've got a breakdown of how many red, green, and blue M&Ms were within the cup, okay? So of those three numbers, we care about the 145. That's the total number of red M&Ms we see in this cup out of 390. Gives us a probability of 37.18%. the probability of B, that we have a chocolate M&M, well, we're going to look at the other marginal distribution, the vertical marginal distribution here, that gives us a breakdown of chocolate versus peanut. So we have 130, not 139, jumping ahead of myself and thinking about the 390. Out of 390 in all, the percent that are chocolate, therefore has to be 33.33%. Okay? So we've got important probabilities here and here. Okay, so what's the probability of, and this is B given A, that is to say, what's the probability that we have a chocolate M&M given that we know the M&M is red, okay? That is separate. Sometimes this, which I'll circle in green, is confused with this up here. Those do not mean the same thing. The probability of A intersect B, which is the top of the two, is saying of the whole collection of 390 M&Ms, what's the probability that I get a red chocolate one? The circled probability is asking us, okay, restrict your view to only the red M&Ms. Let's say we happen to know somehow that the M&M is red. Now what's the probability that it's a chocolate one, okay? So what difference occurs here? Well, instead of dividing by 390, all the 390 M&Ms within the cup, we care to divide by 145 because we're assuming the M&M to be red already. Okay? So, let me go back to my notes here real quick. Make sure I'm writing this as I want to. The probability of B given A is therefore 48, the number of red chocolate M&Ms, out of 145, which is just the number of red M&Ms. Again, this is given event A, given that that we have a red M&M, and that takes us to 0.3310 for that probability. Okay. So conditional probability is defined thusly. Conditional probability is for events. This is for general events, B and A. Don't focus on the red versus chocolate. In that case, why don't I just say this? Probability that event D will occur given event C has occurred is the probability that they both occur. That is to say, D intersect C over the probability of C. Okay? Let's use this idea for the general rule for conditional probability to find this conditional probability above of chocolate given red a slightly different way. So we found it one way, which was to say 48 over 145. Well, using the conditional probability rule, let's again assume B is chocolate, A is red. Probability of B given A is equal to the probability of their intersection. B intersect A, divide by the probability that A has occurred. Well, we found those probabilities, this guy and this guy, we found above. The probability of their intersection, up top, we found to be 0.1231. Okay, divide through by the probability that we've chosen a red M&M, which was 0.3718. And when you simplify that, you get 0.3310. Okay, so we got the same thing here above, just looking straight at the numbers from the table, the 48 and the 145, and what we got below was by analyzing the probabilities. This is generally what you're going to be having to do from the book, although sometimes you can get numbers directly from the contingency table. Okay, so there's conditional probability. Now we're going to get to fixing the general multiplication rule here in this next slide. So we've got the same contingency table set up. We're assuming the same types of M&Ms with the same numbers of red, green, blue, chocolate, and peanut for each. We said, just as a recap from last slide, we've got the conditional probability for chocolate M&M, given that we know it's red, and we have the generalized probability of a red M&M at all. Okay, well notice from the last slide. The conditional probability rule says if we have the probability of B given A to be defined as the probability of A intersect B divided through by the probability of A, that must mean if you solve for this guy right here, that must mean the following. I should stop doing that. That must mean the following, that the probability of A intersect B is equal to the probability of A times, let me actually write that in reverse, the probability of B intersect A times the probability of A. All I did is take the equation on the left, which is our conditional probability definition, and I multiplied both sides by the probability of A, which gives me a fixed rule for multiplication. Notice when we set up the conditional probability definition, we put no restrictions upon using it, okay? As long as you've got the probability of their intersection and divide through by the probability of the first event occurring, this over here has got to be the conditional probability of B given A. So, without any restrictions for the equation on the left, therefore there are no restrictions on our use of the equation on the right. So instead of, remember last chapter, we said the probability of A intersect B would have been this as long as A and B are independent events. Now we're saying the probability of A intersect B is B, probability of B given A, times the probability of A without conditions. Okay? There's no restriction on our use of that. All right, so let's go to the first part here. We've got the first and second parts. Notice we've got the same question twice. And what I want to do here is verify that our new definition, our generalized multiplication rule, works as we would expect it to, using other things that we know from the contingency table. Okay, so let's start with the easier of the two, the probability of A intersect B. Just straight looking at the numbers, we have 48 red and chocolate M&Ms out of a total of 390. So probability of A intersect B is that 48 over 390, which gives us 0.1231. Okay, there's the answer without using our generalized multiplication rule. Now let's use our generalized multiplication rule. The probability of A intersect B has to be equal to the probability of B given A times the probability of A. Okay, so what does this mean? Well, if A has occurred, this must be the probability for B, knowing that A has already occurred. All right, and you just multiply those two things together. Probability for B given A, we had highlighted up here, that's 0.3310 times the probability for A alone, we also highlighted to be 0.3718, which, reducing, or simplifying this rather, gives you that same 12.31%. Okay? So our general multiplication rule works. So we fixed addition, we fixed multiplication, we've talked about conditional probability, at least begun to talk about it, and now in this last slide, we started to hint at independence last slide when we brought up our old multiplication rule. Let's talk about this further. So using the same contingency table, or two-way table, let's refine our concept of independence. If A is the event that we're choosing a red M&M, B is the event that we're choosing a chocolate M&M. All right, so before we said that the events A and B are independent so long as one happening does not affect the other. Let's see if we can write the following and make sense of it. If one event doesn't affect the other, then the probability, for instance, that I have a chocolate M&M, given that I know it's red, so the probability of B given A, that must therefore be equal to the probability that B occurs ever. Okay? Notice what this says. This says when A occurs, the probability that B then happens has to be the same as the probability of B occurring in a general case. All right? That is to say, A does not affect B's probability. A occurring does not affect B's probability. So let's, in this last example that we're going to look at together, let's determine if A and B are truly independent events in this case, that red and chocolate M&Ms are truly independent. Well, the probability of B given A, chocolate given a red M&M, is equal to, we know that from 2 slides ago, I believe, is A intersect B, that they both occur, divide through by the probability that you have a red M&M. Well, the probability that both occur is that 48 over 390 divided by the probability that A occur, 145 over 3. Oh, I don't want to write it quite like that. 145 over 390. This reduces to just 48 over 145, which is, let's find that, 0.3310, and that's your probability of a chocolate M&M given that you know that it's red. Okay? Well, let's look now. Let's see if these are independent events. That must therefore be equal to the probability that of a chocolate M&M being chosen. Well, that is 130. You've got 130 chocolate M&Ms in your cup out of 390 in all, which is a third, 0.3333, and these two things are approximately equal, which is good enough. Okay? Yes, they are independent events. Again, that means the selection or the outcome that an M&M we know is red does not affect whether or not it is then randomly chocolate versus peanut. Okay? That probability is the same as having a chocolate M&M in any case. All right, so there is your start to chapter 15.